Okay, this lecture is entitled The Nested Interval Principle and the Least Upper Bound Property. And in reality, what we're doing here, though we don't do it explicitly, is we're taking the rational numbers and we're creating the real numbers from them. Start out with an axiom, which we call the nested interval principle. And so we have let A0, B0 contain A1, B1, etc., be a sequence of intervals such that the length of the interval from AN to BN can be made as small as we like by taking N to be large enough. Okay. Then there is a unique real number that is common to all of the intervals. Okay, so again, these intervals, we start out with the biggest and we go down and it gets smaller and they're made just teeny. Okay, and so they're nested within each other. We call this the nested interval principle. Okay, so let's step here in something which is related. We call it the least upper, we're working towards the least upper bound property. Definition, let S be a subset of the real numbers. Let U be a number such that U is greater than or equal to S for every S in the set. We say that U is an upper bound of S if we say that U is an upper bound of S then, because it's bigger than everything in it. Now, if L is a number that is an upper bound of S and is such that L is less than or equal to U for any other upper bound of S, we say that L is the least upper bound of S. Okay, so it's an upper bound and it's the smallest of the upper bound, so it's a least upper bound. The nomenclature works, and we'll write here that L is equal to lub, which is least upper bound of S. Okay, now this axiom is an alternative axiom to the nested interval principle. We say that S has a least upper bound property if whenever T is a non-empty subset of S and there is an upper bound U of S in S for T, then there is a least upper bound L for T, which is an element of S. Okay, so each non-empty set that has an upper bound will have a least upper bound. Okay. So we have two axioms. Okay. And what we want to show is that they're equivalent to each other. That whenever we have a system that has one of these axioms, we can use the other just as well. Let's start out with the proposition: a set of numbers has the nested interval principle exactly when it has the least upper bound property. And we're going to start out assuming that we have a set of numbers that satisfies the nested interval principle. Okay, now suppose we're going to then show that it has the least upper bound property. Suppose that T is a non-empty subset of S that is bounded above by the number B0. Okay, since T is non-empty, there is an A0 element of T. Okay, now this closed interval A0 B0 is a closed interval with two qualities. Okay, and these two qualities we're going to iterate through a sequence of intervals. Okay, the upper end point of this interval is an upper bound of T, and the interval itself contains points of T. Right? Upper interval is upper end point is an upper bound, and it contains points of T. Hold that in your pocket right there. So we have, I've drawn a picture of the interval. So let M be a midpoint of this interval. Okay. Now either m is an upper bound of t or it isn't. There ain't no third way to do this. If it is an upper bound of t, then a naught m contains points of t, and it has an upper endpoint that is an upper bound of t. And so in this case we would let a1 equal a naught and b1 equal m. Now on the other hand, if m is not an upper bound of t, then the closed interval from m to b naught will contain points of t and has an upper endpoint that is an upper bound of t. In this case, we let a1 be equal m and b1 equal b naught. But in either case, we will have an interval, okay, a1 b1 that contains points of m and whose upper endpoint is an upper bound of t. Okay, so we've got things set up so that we can continue in this way and get a sequence of intervals. Each one is half as long as the last. Each one contains a point of t, and each one's the upper endpoint is an upper bound for t. By the nested interval principle, there is a unique number c that is common to all of these intervals. Okay, we claim c is the least upper bound of t. Okay, so let's check this. So if c fails to be the least upper bound of t, then there is some little t in t that's bigger than c. If this happens, choose n so that the length of an bn is less than t minus c. In this case, we have an is less than c, is less than bn, is less than t, but bn is an upper bound of t, so this is a contradiction. Okay, so therefore c is going to be an upper bound of t. Now, so let's check that this c is less than all of the other upper bounds. Suppose that u is an upper bound of t. We claim then that u is bigger than c, because otherwise c is going to be bigger than u. So now we choose n so that the length of an bn is less than u minus c. This means that u is going to be less than an, is going to be less than x, is going to be, okay, where did x come from? Excuse me, less than c right here. Okay, typo, is less than or equal to bn, and so as bn must contain points of t, this is a contradiction. Okay. So having proven things in one direction, let's flip it back and take it in the other direction. Let's assume that S has the least upper bound property, and we're now going to show that it has the nested interval principle. So let's have these nested set of closed intervals whose length can be made as small as we like whenever n is made large. Okay, so let's find a single common point to these intervals. Let t be the set of all lower endpoints of the nested intervals. Then each bn, okay, is an upper bound for, and again I've got a typo here. There should be a closed parenthesis here. Okay, is an upper bound for t. So let L be the least upper bound of t. Okay. Okay, so L, this L is going to be the common point we're looking for. Note that L is greater than or equal to every an, and note that L is less than or equal to each bn, and so this L is in each of the intervals. Okay. Now, so it is in each of the intervals. Now the question is, why is there no other number common to all of these intervals? Well, it's because if there were another number, there would be a positive distance apart, and you could choose the intervals to be smaller. So we're cool there.